Okay, and then over here, there's also another point that says decision trees are non-parametric supervised learning method used for classification and regression. Okay, so this is a point I wanted to highlight on, that in the first instance of our introduction to decision tree, we saw it being used for classification, and that's where I think we brought back the iris flower data sets. But then in this instance, we are going to see how we use it for regression. However, the mathematical foundation and the principle for decision trees um, does not change as far as those things are concerned. So we are not going to go back to some of the things we spoke about earlier on. They are almost the same. So we are going to continue from there to actually go straight to the model development. But it's not just decision tree classifiers. Same can also be mentioned or said about the random forest. Remember what we said, that the random forest is an extension of the decision tree. So if we can actually use the decision tree to do classification and regression, then we can also use a random forest to do classification and regression. We can also use the support vector machine we saw earlier on for regression as well. So in this particular lecture, we are going to see how we use those, for instance, the decision tree, the random forest, the support vector machines, okay, these three in particular for regression models. And whether we do classification or regression, I want to just ask audience a few questions. What is going to inform us to either do classification or regression? Just a quick answer. Anybody can help us. Hello. Okay, Sheriff, you can proceed.
Please, can you ask the question again, please?
Okay, so the question is, if we can actually use, for instance, decision tree for either regression or classification, then what is going to inform us to use decision tree for regression or to use decision tree for classification?
So I think yes, if the output we are expecting is numerical, we will use yeah. I think if you are expecting a numerical output, it's good to that will inform us whether to use the
Regression. Okay.
yes, the
All
regression.
right. Thank you very much. And I think Mariama had it in the chat that whether the target is numerical value, then we go for regression. So that's perfect. But then when the target has some kind of class value, and when I say class value, remember in the case of the iris flower, we had three classes. We had iris setosa, iris virginica, and iris vesicular. So those were those ones, okay? But in the case of the regression models that we are going to use the decision tree algorithm to build, we are going to look at values or the target values or the Y output being some numerical values. Okay. So having said that, let's see how we do that quickly, because we are going to build three models and we are going to do a comparison of these models. And that's going to be a very good exercise because, like I always say, if this is some kind of a project work you are working on, you would want to have about 3 or 4 models, and then you do a comparative analysis of these models and whichever one which is giving you best performance. So I'm starting the Jupyter Notebook environment, and then we are going to go straight into whatever thing we need to do. Okay, so I'm going to open a new notebook. And let me rename this because I have quite a number of them. So let me have this as regression. Okay, so we do the import of our libraries, and the first one we are going to have is NumPy as NP. And then for starters, let's say we are going to, okay, so from matplotlib, we are going to import pyplot as PLT because we are going to do some plotting at the end of the day. Then for now, let's import sklearn and import sklearn. All right. Okay, I should have even done this straight ahead. So let's look at the data set that you'll be working with. So from sklearn.datasets, would want to import, there's a data set. So if we are to do the load iris, that's the name. If you are to do the load iris over here, and then if you are to have data is equal to load underscore iris this way. The moment we do a preview of this, we see that yes, we have the data showing up over here, but then the output, Kelvin is asking if the screen is being shared. Well, as far as I'm concerned, it is. Is anybody else not seeing my screen? Okay, let me see. But okay, so Miami says I can see, please. Okay, so I believe maybe it's the network somewhere along the line. But then for the benefit of everybody, let me just stop sharing and share back again. Kelvin, is it better now? Well, if it still persists, then I believe maybe it may be from your end because others are seeing it or are seeing my screen. Okay. All right. Okay. So just to have a recap and also so that we don't move too fast, okay. We are clearly seeing that when we load this iris data sets, we have the actual data, which is going to constitute our X component or our X part of the data. And then when we come down to the target, we see that we have zeros representing one class, then all the ones over here representing another class, then all the twos also representing another class. So these were some of the reasons why that informed us to use the decision tree classifier for the classification task. Now, in other data sets, like there's another one called the diabetes. So it is still in scikit-learn inside of the sub package called data set, and there's the data. Okay, so when I run this, and then what I'm going to do is I'm going to load this data set as I have it over here. So you could see that the format and also how we put things about is almost the same. But in this particular instance, when I run this, you see that this is the component, the X part of the data. And then clearly you can see that for the target, we have some numerical values showing up over here. And they mean something, okay? Now, in order to help us understand this very well, we are going to go down to, there's a description part of this entire data frame, okay? So what I'm going to do is I'm going to have data and I'm going to slice and get the description so that we can read a little bit about this data. Okay, it doesn't look too good, but then I think if we are to print it this way, then it looks a little bit formatted and everything else looks good. So this is a description of the data set. This is a diabetes data set. So it says 10 baseline variables. So there are 10 variables basically. We have the age, the sex, the body mass index, the average blood pressure, and the blood group serum measurements were obtained for each of the N the number or the sample size, which was 442 diabetes patients, as well as responses of interest. Now, a quantitative measure of the disease progression for 1 year after baseline. All right. So these are the data set characteristics. The number of instances is 442, and the first 10 columns are the numeric predictive values. So that's going to form part of the X component. And then the target we see is column 11. So it is a quantitative, okay? It is not a qualitative to tell us whether it is diabetic or not diabetic. It is a quantitative measure of the disease progression of 1 year after baseline. So if we had, for instance, maybe a medic, they are quite knowledgeable in these matrices to tell us exactly what is happening. But let's just understand it the way it has been presented to us, that they are saying that for the column 11, which is going to be our target, it is a quantitative measure of the degree disease progression 1 year after baseline. So we see that these are the attributes information, as we can see over here. So these ones are well noted. Now, each of these 10 feature variables have been mean-centered and scaled by the standard deviation times the square root of n samples. And that is the number of squares of each column, total 1. Now, what is happening is, for instance, in mathematics, okay, sometimes if you have, let's say, a system of equations, so let's say you have 2x plus, let's say, 4y is equal to 10. Now, what you can do is you can scale this up. And when I say scale this up, you either you can scale down, okay? So either scale up or scale down. And when you scale down, you can, for instance, divide all the terms by 2. Now, when you divide all the terms by 2, you end up getting something like x plus, please, we are getting feedback. Okay, x plus 2y, and this is equal to 5. So this is we scaling down, okay? We can, for some funny reasons, we can also scale up, and that will probably be multiplying through by maybe a factor of, let's say, 3. So if you are to do a scaling up and multiplying this by a factor of 3, then you're going to get 6x, okay, 6x plus, we'll get a 12y over here is equal to 30. Now, I'm using this because at least these are simple algebra things that we know to explain something over here. Now, the point is, when we scale down, okay, this equation as it stands, as compared to this, and as compared to this, mathematically are the same. That's the point I want to make, okay? Mathematically are the same. It's just a matter of scaling up or down. Now, what we have over here with our data, and it's good, this information is being shown and is being putted out over here, that you should note that each of the 10 feature variables have been mean-centered and scaled by the standard deviation times the roots of the number of samples. So the number of samples we know is, from what we see over here, is 442, okay? So that's what we have been told, because eventually you can see that the first, for instance, the first attribute we see over here is age. Okay, the first attribute in the data is age. Now, if I'm to go into the data, this is the data. Let me clean what I have over here so that I believe we understand this. Okay, so what we have over here is the data. Okay, so now if I'm to do, for instance, data and grab this data, we get the actual data. So if I'm to do data and slice and do this data, we've seen this over and over again. We get the actual X components part of the data. Now, if I'm to grab, for instance, the first instance of the data, this is what I have. Okay, and the first instance, clearly we see that we have some values showing up over here. All right. Now these values we see, for instance, the first one, if we are to count, we are told that it is 10 in all. So here we have 1, 2, 3, 4, 5. So top and down, they are 10. But then you can see that we have a 0.038. Now this 0.038 ordinarily is supposed to be for the age. But then if you don't read what we have over here in terms of how the scaling was done, then it will become very difficult trying to explain, why is this happening? Now, the point is, it says that what each and every one of them, each of the 10 features of the variables have been mean-centered and scaled by the standard deviation times the root of the n samples. And that is the sum of squares of each column totals 1. So that's what is basically doing. So basically, when you sum everything up over here, we are being told it is supposed to total 1. Let's try that and see. So if I'm to do np.sum, np.sum, looking at the numbers, well, let's see. We don't get the 1 over here. Let me see what that means. The sum of squares of each column okay, the sum of squares of each column. So let's do the sum of squares. The sum of squares of each column. So first of all, let's do this. And if you have to do the square, okay, so let's square everything and then the sum of those ones. So if I'm to do this multiplying by itself, that's the square. And then if we are to, let's say, np.sum and run this, we are still back to what we saw earlier on. Let me see this. Control C, Control V. 0.4. Okay, these two are completely different. All right, so I think the formula, the sum of squares of each column equals 1. All right, so let's see the data itself. So the sum of squares of each column. This is one column, this is another column, this. So the sum of squares. So let's say I pick the first one, which is this value, and then square it up, and sum of squares of each. Well, I'll look at this very well, but then we get the point. Some scaling has been done, and then based on that scaling, affects all. So the scaling factor runs through, and that is why we don't necessarily see, for instance, age. We don't see like 50 or 100, but then we see some numbers that ordinarily may not look like the typical age that we know. Okay, so this is original data that we have, and this is what we are going to work with. All right. Now, there are other things I would also want to touch on. Yes, so these are some extra readings you can do, and this research was done by the man over here in 2004 and at Stanford. So this some data that's been verified, and scikit-learn has it inside of its repository of data sets. So this is what we are going to use to work. Now, what I also want to do is, if I'm to do data and grab the targets, okay, this is a original data set, okay, and grab this target, do a Control C. We clearly see that these target values are not um, class based, okay? These are numerical values, and for which reason we can build a regression model out of. So the point is, given the first instance of the data, okay, its corresponding target in terms of numeric value is 151.0, as we can see over here. And like I said, the age, the blood pressure, the body mass index, and other things have been scaled. So looking at it numerically from this standpoint will not make sense unless we do that scaling. All right. So given this, we are saying that the target is 151. And this target, we've been told that it is a quantitative measure of the disease progression on 1 year after baseline. So like I said, the medics are the ones who are going to probably tell us what this 151 actually mean. But then let's move on to build our model and see how things will work. So originally we have our data this way. Now we want to get the inputs and the outputs. So what we do is for the X input is going to be equal to this data, and then we grab the data column. So if I'm to do a preview of this, this is exactly what we have for the X input. Now let's do the Y output. So the Y output is also going to be data, and then we grab the targets. So if you are to do a preview, we get to see these big metrics showing up over here. All right. So we have the input and the output. Now let's look at the other things that we need. So in this particular instance, we have a good amount of data, okay? Because remember, even with the Iris Setosa, I mean, the Iris data set, we had about 150 instances, okay? And then we're even splitting it into the training part and the testing parts. So this one too, with 442, I think we can do same. So over here, I can say from sklearn dot model underscore selection, we would want to import train test split. All right. So I'm going to do xtrain x test, then y underscore train, then y underscore test should be equal to, then we can bring this down and I'll pass in our x inputs and our y underscore output. And then let's specify a test size of a 0.2. So now everything looks good. We can now use this for the training and then use the testing part for the testing. All right. So we don't have to, but then for the purposes of this, we can just do a preview of this. And if I'm to do the dot shape, so that we see exactly what we have over here. So clearly you can see that the columns are 10. And from 442, 80% of it, probably, let me see, 0.4, sorry, 0.8 multiplying 442. So we get exactly that, okay? That's the 53 instances we see over here. Okay, so everything looks good. Now let's look at building the model itself, because working with the data, we are quite familiar with. So I'm going to say from sklearn dots. Remember, okay, so let's start with the decision tree, okay? So from sklearn.tree, earlier on, we imported like there's the decision tree. Good. So over here, we have two options. If it is a classification, we can use the decision tree classifier. But this time around, we are doing a regression. So we can do or import the decision tree regressor. So this is what we need. And this is going to be the framework, the algorithm for which we are going to create that regression model. So I'll run this. And now I'm going to say model one, because we are going to build, or okay, let's call this DT underscore model. So that's the decision tree model. Is going to be equal to, just as we did before, we just bring this and, sorry, we just bring this and instantiate it this way, okay? So this is going to be the decision tree, and not the decision tree classifier, but then the decision tree regressor, okay? Because we have some numerical data for our outputs. So this one looks good. And then let's run this. Now I can do the DT underscore model dot fit. Now, what do I want to fit? I want to fit. And once again, I always do this just for reference, okay? Because it is important we do that. So these are data sets. And then per our data set, we have columns and rows. Now, based on the columns and rows, we said this part, let me use this. So this was, for instance, maybe the original data set, okay? Now, this is going to be the X component. So these are where we have the columns, the age, all those things over here. And this is where we have the targets, which is some numerical values. Now, what we did in terms of the train test splits is we have divided this into some training parts and some testing parts. And we have about, we have about 20% for the testing parts, 20% for the testing. So a big chunk, as we see over here, is going to be the training part. So this is going to be our X train, this side of the data set, okay? And then this side of the data set is going to be our X test. Hey, sorry. This is going to be our Y train, sorry. Our Y train. Now, what we have over here is going to be the X test. And this side of the data is going to be our Y test. All right. Now, there's a reason why I bring this all the time, almost every time when I'm building some of these models, because I don't want us to miss out on anything. So what we need is, okay, we are going to use the X train. Let me bring this. We are going to use the X train, okay, and the Y train to train the model. And then when we are done, we have some kind of a model over here. And then we are going to pass in the X test, which was not used for the training. Now we are going to use the X test to make some predictions. So we are going to have some predictions. So let me call this P. And those predicted values will now be compared with what we have in the original Y test. And at the end of the day, we'd want to check the variations. So remember when we're dealing with the linear regression the last time, it was the variation from what was the actual and what was predicted. And that's why we were looking at the mean squared error and all those things. So that's what we are going to do over here. Nothing has changed. So what we need is the X train. So I'm going to put in X train. And then we need the Y train as well. So Y train. And I think that's just about it. So X train, Y train, let's run this. And now this model has been built. We don't seem to have any problem. Good. So now if I'm to do model.predict, and now pass in the X test, because that's what I want to use to check. And let me save this in a variable called predicted values or something like that. Okay, Sharif, I can see your hand up. Is there any question?
Please, the DT model.
Oh, okay, yeah. I think I'm carried away with always using the variable name model. Okay, so for emphasis, the name of the model over here is DT underscore model. Thank you very much. So we have this, and if I'm to run this, yes, that predictions or those predictions have been made. That's what we are going to have over here. And we are going to compare those values with the Y test. So if I'm to bring this down over here, okay, some values have been shown up over here. Now let me also put in the Y test, which is the value I see over here. Okay, So things looks a little bit interesting over here because, for instance, if you have to compare the first value, let me also do some slicing and let's say grab the first 10. So I want to just get the first 10 over here and also just get the first 10 over here. All right. I think at this point I can clean whatever thing I have over here so that we can concentrate on the values we are predicting. Okay, so things are looking a little bit interesting. You can see that clearly with this. With this one, the predicted was 163. The actual was 232. There's some wide variation showing up over here. This one was pretty close, okay? Just a variation of 2. So the actual was 68 and the predicted was 66. This one too, there's some wide variation, okay? About 23, I believe. Over here to this much, I mean, this is very wide. This pretty close, about 9. And it goes on and on and on. But at least some prediction has been made and we can see some few things showing up over here. Now, what you want to do, like I said, the numbers you would understand, but then there are a lot of people who may not understand these numbers. You need to put some graphics for them to appreciate what you have and how things are going. So since we have imported, I think matplotlib over here, let's work out on some plots. So when I do, for instance, plt dot scatter, and I pass in the actual data. So the actual data I passed in was my X train and then my Y train this way. It says X and Y must be of the same size. Oh, okay, sorry. X train, X train, Y train. Y is, let me check some few things over here. So X underscore train dot shape. Oh, okay, okay, okay. Y underscore train dot shape. Oh, okay, okay. No problem. Let me see if um X train. Okay, let me see the issues of the shape. We have something like this. We have for the X train, we have 10 columns. Okay, so we have 10 of these things, and then with just one Y. So if we are plotting this, it becomes a little bit of an issue. Okay, just plotting it just like that because this is not going to come. It is more or less going to come like um, um, a bunch of numbers put together one way or the other. Okay, as against this one coming in as a single digit kind of. I don't know if that makes sense. All right. But I think there's a way we can go about this. Let me just see. Um, okay, so let's do plt.plots. And let me just do X train and then Y train. Wow, there's a lot of unwanted numbers over here. Okay, so let me just do this. Hmm. There's a lot of things I don't need in this particular one. Let's see, PLT. Okay. Okay, we are plotting our X and our Y. And then X train, Y train. Okay, okay, okay. So let me plot, I'm thinking of X, Y train. I get confused with this all the time. We have X train over here, and then the Y train. We have X test, and then the Y test. Okay, so let me just plot Y train, Y test over here, because these are the actual values. What are we saying? Oh, okay, so there are dimensionality issues. Okay, I mean, obviously. All right. So these ones too. Okay, let me do 89 over here. Let me do, let's say 80. And let me do 80 over here. Okay. So this is not looking bad. This is just the Y part of the data. Okay. And now what I want us to do is to also plot the predicted, okay, the predicted versus the test to actually get the regression line and see how things are beginning to line up one way or the other. Because we are always going to compare the test with the predicted. So this is the plot. If I'm to do PLT dots, another plot, and then now do the, sorry, the Y underscore, let me call these values, Control C, Control V, and then the first 80, and then the tests. So Y underscore tests, also the first 80. And then what is happening? The predicted versus the Y tests. Okay. Let me just give this, no. Let me also use the dot over here. And then I believe, okay, so from here we get at least some graphics to show some patterns over here, okay, except that it is not too clear, and I'm getting a little bit confused, to be honest. But then let's see what we can make out of this. Clearly, we are plotting the actual and also doing a direct comparison with the real data that was actually used for the training and testing. And then we see that, okay, there are some similarities around in terms of where the thing. For instance, if you have to zoom in very well, look at this particular one, okay? The first blue is the actual, and then the yellow we see over here is the predicted. It tells you how close, for instance, this prediction was with regards to what was predicted and what the actual was. We can also make a case for this particular one, okay? Tells you how close we were. And then there are some few ones. Some, I think they are overlapping or overlaying on top of each other. So it will be very difficult for us to make that comparison. But then we get the point that these are some of the things we can see over here. Now, what I want to show is also the mean squared error and the R squared error. these are things we spoke about the last time. So what I'm going to do is I'm going to say from sklearn dot metrics, I would want to import the mean squared error and the R squared error this way. And then we have, this is, okay, it is R2 score, sorry. Yeah, the name is R squared error, but then the way scikit-learn has it over here is R2 score. Okay, so now we can bring in those things to actually see. So the mean squared error is now going to be equal to this, and then we pass in the actual and the predicted. So we can come back here and then this time around, we don't need to slice everything. I mean, we can use the actual thing over here. So if I'm to do a printing of this, we get this value. Okay, good. Now let's look at the R2. So this is the R squared is going to be equal to this, and then we pass in this and this as well. And then we get to see this showing up over here. So over here, we get some negative, very small value over here. All right. Now, this is just for the decision tree, okay? If you are to continue with the, how do you call it? The random forest, and I'm just quickly going to do that. We are going to build that in a matter of seconds. So over here, it is from sklearn.ensemble. Want to import, and then we want to import the, sorry, the random, sorry, sklearn.ensemble. No, I think the spelling over here is wrong. Ensemble, okay. We want to import the random forest. Let's get some help over here. So we have, once again, we have the random forest classifier, which we've seen earlier on. And then we have the random forest regressor, which we are going to see. And then you see that we have the random trees embedding. I think later on we are going to come back to this if there is time, because there are some parts of, very good. You can see that we have ensemble learning algorithms over here. All right. We can design our own structure things, but then the random forest gives us the opportunity to have ensemble learning right out of the box. So we want the random, sorry, the random forest regressor this way. So we have the other parameters. So let's quickly move on to this. So to do random forest, so RF model is going to be equal to what I have over here. And then we instantiate it this way. Then we can have the RF model dot fit. And then we pass in the values just as we did earlier. So X train, Y train over here. Okay, so we can now do a prediction. So I can do this dot predict. And then we want to pass in the X test. Sorry. It is capital X. All right, so now let's save this in a variable, let's say RF underscore prediction is going to be equal to this. Now, the thing we always have to do is to now compare, but then let me just slice in the first 10, okay? And I'll compare it with the Y test, which is the actual Y values, and also slice in the first 10. Oh, sorry, the first 10 and not the 10th. So clearly you can see that This one too is giving us something to think about, okay? In the sense that we have 205 for the predicted, and then it was 232. This one was way huge in terms of the variance between these two. We have something which is significantly huge for the third one. And for the fourth one, it is also huge. At least just by looking at this, we can tell that this is not doing so well. Okay, except that we have 85 over here. That's the last but three. One, two, three from behind. When I do one, two, three, we have 84 over here. So this one is matching up with this one very closely. The one we have here is 156. This 150. Okay, it's not too bad. So at least we can see that there are about two of them that were okay in terms of the variance, okay. But then the rest of the other ones we see clearly are too huge. Now let's also check, for instance, if I do a negative 10, definitely the last 10, okay? So let's check the last 10 and just, uh, I wasn't expecting to see everything over here. Okay, let's do from 10, starting from 10 and ending at, let's say 20. Starting from 10 and ending at 20. So let me run this and come in here. Okay, so this one was 111. The actual was this. This one too is quite huge. The difference. Let's see if we can spot some few close ones. I think this one probably might be the closest, 133 to 113. And then there are some few ones that are on and off in terms of the variance. Okay. All right. So just at the back of this, I get a sense that the random forest is not doing too well, but then we can only make that conclusion if we actually check with the mean squared error and also the R squared error to actually make that final determination. Just a minute, I'm plugging my charger to charge my laptop. My battery is running down. All right, so I'm back. So once again, let's do the um, random forest underscore mean squared error is going to be equal to the mean squared error we have over here. And then we pass in these ones, the predicted and the test, the actual. So if you had to do this and now run this, all right, now if you had to do a comparison with this and the one from the decision tree, um, I don't know, the values are the same. Um, okay, let's look out for the R squared. So let me just copy this. I don't know, maybe we are missing something else where, but let's see. There's going to be the, oh, no, 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 no. So the predicted is actually RF predicted. I'm still passing in the predicted values, which is for the, how do you call it? The decision tree. That's why we are getting same value. So when I run this, good. So you see that the mean squared errors are different over here. Later on, we are going to see what it means to have maybe something like this as compared to something like this. And that's going to help us make a decision. So let's look at the R squared error for the random forest. So let's call this RF squared or squared one way or the other. And then we pass this over here. And then when we check the actual value, we see this over here. So this is also giving us something negative. If you have to compare it with its compatriots, as we have over here, it is also in the negatives, but clearly we could see that there are differences over here. This is for the decision tree and this is for the random forest. So definitely the most important thing for us now is to actually analyze what these numbers are, what they represent, and how we can confidently say that, okay, this one is better than the other one, which we are going to come back to because that's the main purpose for whatever thing we are doing today. Now, the last one, obviously, let's build is let me see, is with the support vector. Over here, we have classifier. So we would want to build the support vector regressor. All right. So let's build that one quickly. So I'm going to call this SVM. It's now SVM model is going to be equal to, sorry. First of all, let me import it. So I'm going to say from sklearn dot svm. I would want to import, and then earlier on we have some options over here. So we have from SVM, I want to import S. Very good. So you see that we have the SVC, which is the support vector classifier. And then we have the SVR, which is the support vector regressor. All right. So this is what we need for at least the regression. And for some funny reasons, let's assume we are just doing plug and play without even knowing exactly what is happening. What I'm going to do is we are going to play the devil's advocate and actually use, for instance, maybe this data set to actually try and see if we can build a classification model out of it. And definitely we are going to get some errors, and those errors are going to inform us that, okay, we are doing the wrong thing and stuff like that. So we are going to look at that after this one. So we call this, and then let me call this SVM underscore model. And that's going to be this. And then we instantiate it this way. Now I'm going to say this dot fit. And then what I want to fit is the X train, Y train, this as well. So Control C, Control V over here. All right. So now let's do the prediction. So this model dot, sorry, dot predict, and then we would want to predict using the X test. And let's call this SVM underscore prediction. So I ran this, and now let's just have a preview. So, and let's just get the first 10 values, okay? And let's get the actual Y test to also do the comparison. Also, let's get the first 10 values. Okay, so over here, we get to see that the actual is 232, but then the predicted is 157. Okay, over here it was 86. The actual, we predicted this, and then this one was 137. The actual was 114, and it goes on and on and on. Okay, I'm trying to figure out maybe one that was a little bit close. I think it would be between these two. So let's count from behind. We have 1, 2, 3, 4. The fourth from behind. So you have 1, 2, 3, 4. So I think the fifth from behind is what we have, the 140, and then the actual is 154. So this, I believe, was the closest, and there are some few ones that we can also look at later on. But then once again, let's look at uh, the mean squared errors and all those things. So once again, let me copy this one. And then we need this prediction over here. Oh, sorry. SVM. All right. We have an interesting value over here. Let me, all right. So let's do and check this one too. We are getting this showing up over here. So at least there are some interesting values we are seeing over here. And then we can go on and on and on, okay? We can actually put this in a data frame to make it look cool, or even some kind of a dictionary kind of, okay? So let's see, we have a dictionary called results, and then the key value pair. So I can look at SVM underscore, let's say the mean squared error, and the value is actually going to be this variable as we have it over here. Okay, then I'll do a comma. Then let's have SVM squared, whatever. And the value is also going to be this. Then we can go on and on, okay? So that at the end of the day, if we are to print results, it will kind of look decent, okay? We can actually, let's say import, sorry, pandas as PD. Now I can do PD dot data frame and then pass these results data frame over here so that we have like a nice table. It says if using all scalar values, you must pass an index. Why? Okay. So data axis. Okay, so I think axis is equal to this. No, it is asking for axis. Let me just get rid of this. All right. So we can get to see these values printed out over here. But then, like I said, the main thing we want to do is a comparison between why will I say this is better than, for instance, the RF underscore mean squared value. Okay. Why will I say, okay, this one has overwritten that. Oh, let me run everything once again. Okay, in a matter of few seconds, everything good. All right, so yes, the big question, why will I say this, for instance, which is the SVM mean squared error, is maybe better than this, or this better than this, and stuff like that. These are the things that would want to see in terms of whatever thing that we have. So let me just try and print everything all together so that we have it under one roof. So SVM mean squared error. Let me use a formatted string over here. Okay, so this is the R square. So let me say R2, and that's going to be this. So let's get this for the other classifiers, regression models that we have built. So this one is going to be for, let's say, the random forests, and then decision tree, decision tree. So let's look at the variable names we use over here. So RF, okay, this one, and then the RF scored. All right. So RF, and then the RF scored, and then the decision tree. I think that's the original one. We use the R scored and this one. Okay. So R2 scored. All right. So I think, yeah, these are the ones that we see over here. So like I said, we are trying to do some comparison over here. We have for support vector machine. Remember, it's the same data sets. We use default parameters. So a lot of things are not changing up over here. But then clearly we see that, for instance, with SVM, the R squared error, we are getting a negative 16 over here. But in the case of random forest, in fact, in all of them, you are getting a negative, or we are getting negative values. But then we are seeing a very big gap over here as compared to what we have. These two are very close. Okay, remember, for decision tree and random forest, like I said, one is an extension of the other. So they are most likely to give you very close results. But then in the case of support vector machines or support vector um, regressor, it is giving us something which is very wide. So let me just do a Google search on this in order to back my explanation. Now, let's say mean squared error, um, high and low values and their meaning. All right. Now let's look out for a very credible source to actually base our explanations on. Mean squared error, high and low values and their meaning example. Oh, it's giving me the same thing over here. Okay, let's go to Britannica. Now we get to see that, of course, we know that is the average difference between the value observed in a statistical study and the value that was predicted. And that's what we said over and over again, the variance between them. Now, when comparing observations with predicted values, it is necessary to square the difference, as some data values will be greater than the prediction, so that their difference will be positive, and it goes on and on. But then let's look at this, and I think this formula is what we discussed the last time. Now, in terms of the value, we are saying that if the prediction passes through all the data points and the mean squared is okay, so if the prediction passes through all the data points, then the mean square is 0, because then in that case, the variance, there's no variance, so it is 0. Now, as the distance between the data points and the associated values from the model increases, then the mean squared error increases. Thus, a model with a lower mean squared error more accurately predicts dependent values from the independent variable. So the point is, the lower the mean squared error, then the better for us. Let me repeat that. It says that's the model with a lower mean squared error, because at the end of the day, I think I explained this the last time, but let me just touch on it again. At the end of the day, it is a variance. Okay, we had some predicted value, and our regression line was, let's say, um, we have some predicted value, and let's say this is the actual. So this is the predicted, this is the actual, and the predicted is going to have that that regression line passing through. So now the point is, what is the difference between, or the variance, okay, between the predicted and the actual? Now the point is, if it is 100% accurate, then it is actually going to overlap on the same spot. So the point is, if there's a difference, then the smaller the difference, the better for us, in a sense that in the case of what we see over here, we see that the mean squared error value for support vector machine, okay, I mean, they are all big, but then relatively, this one is smaller than this for the random forest, and also smaller, far smaller than this for the decision tree, which is very obvious as we see over here. Good. Now, let's look at the situation for the squared error. So we can go on and on to read on this. Now, we have an instance with the, okay, that's not what we need over here. This is basically showing the formula, and I think we calculated an example last Friday. Okay, let me clean this up because there are some extra readings we have over here. It says that, however, what can be done in this particular example is to compare the predicted value for the various years, and we had the mean squared error to be 8 points, whatever. Okay. So this is based on the data they had and the things they are trying to explain over here. Now let's look at the R squared error. So the R squared error, high and low values and meaning. Okay, so it says for the same data set, a high R squared value represents smaller difference between the observed data and the fitted values. Now the R square is a percentage of dependent variables. Okay, so over here, right? So over here we have let's see some other detailed explanations to whatever things we are looking for in here. Okay, so it's lower R square are generally desirable. Okay, so in the case of no, this still mean squared error. Okay, so this one is what we covered earlier. I don't know why mean square. Let me go back. Okay, R squared meaning good. Let's see what this one. All right, so it says, what does R squared look like? So it is a percentage of a range between 0 and 1. Now, R squared of 0 means the independent variables don't explain any of the variation in the dependent variable. And if it is 1, it means that it is perfect. So over here, the closer we are to 1, the better for us. So it is almost like a counterintuitive nature in terms of how the mean squared error works, because with the mean squared error, the smaller the better, but this one is almost as if the bigger, in this case, the better. All right, so now when we come back here, when we actually to compare these ones, okay, these are the R square errors. The question we are asking ourselves, okay, this one, if it is big, it is better. Okay, if it is big, it is better. Now the question we ask ourselves in terms of value, um like in terms of values, okay, in terms of values, is a negative 16 better than a negative 0.7? um, I mean, is it bigger? That's the point I'm trying to make. Is it bigger than a negative 0.46 as well as a negative 4.44? Okay, those are the questions we need to be asking. And to make this very simple, let's go back to first principle. We have 0 over here. If we are moving towards this side, we are getting bigger. Is that okay? When we move towards this side, we are getting smaller. So for instance, 1 over here is bigger than 2. We are moving towards this side. Then over here, we have, for instance, a negative 1 and then a negative 2. When we go this side, we are decreasing, we are getting smaller. So definitely a negative 16 will be somewhere here, far to the left. And then a negative 0.44 will be somewhere here. So at the end of the day, which one is bigger? In this case, to make things very simple and also visually explanatory, the negative this value is bigger than this value as we have it over here. So at the end of the day, this becomes more desirable than what we see over here. But then once again, for those of you who are very observant, it is almost as if, okay, if that's the case, it does appear that in the case of these values, the mean squared error, we want the smaller, okay? And then in the case of this one, it is almost as if we want the bigger, relatively. But then over here, this is the smaller, this is big, but then when we turn it around, this is better than this. I don't know if you get the point I'm trying to make over here. In terms of the mean squared errors, this value over here is better than this value. But then in terms of the R squared error, this value is better than this value. So in that case, the big question is, what then do we go for in terms of this? And this is a very good example for us to actually analyze, okay? And also see exactly what we are working with. So now this is what I would say. Now, in most cases, there's always going to be some kind of how do you call it? Um, a pattern, okay? And the pattern probably most cases is going to be like, if mean squared error is good, its corresponding R squared error will also be good as compared to the other models you may be comparing with. Generally, or ideally, that's how it's supposed to work. But in some instances, you may have kind of conflicting one on one leg saying I'm better than you, but then on the other leg, the other person too, or the other metric too is also saying I'm better than you. So once again, let's go back to what we are doing. So we are seeing that mean squared error and R squared error, which is more statistically relevant. Okay. Okay. So it says you see if the data set contains outliers or extreme values that might disproportionately affect the model's performance, you may prefer R squared with less sensitive outliers. All right. So now I think this one, based on the explanations that we've done over and over again, this one is making a lot of sense over here. So now let's go back to this. It says that what if there are outliers or extreme values? Because remember, if we are to plot our graph, okay, and let's say these are the original data points that we have. Let me have this a little bit bigger. These are the original data points, okay, and there's an outlier way over here. If you are fitting a regression line, okay, you realize that the um the mean squared error, which is actually going to fit this regression line. Let me just show. Let's assume this is a regression line, and maybe there's an outlier. Let me put one over here, which is way too away from the regression line. Remember, it is going to be some predicted value. So the corresponding predicted value may be somewhere here. So it's going to be the variance between this and this. So because of this outlier alone, we are going to have this hurting our mean squared error. So then, back to the point, if the data set contains outliers or extreme values that might disproportionately affect the model's performance, you may prefer R squared, which is less sensitive to outliers, because clearly you can see that for the mean squared error, we are trying to calculate the variance between the actual and then the predicted. Everything predicted will be on this line, and the actual is actually going to be plotted. But then in the instance, it says the mean squared error, on the other hand, is sensitive to outliers because it squares the difference between the predicted and the actual value. That's what I just explained. Okay, it squares the difference or the variance between the predicted and the actual value. So once again, a lot of these also lies in the kind of data set you are working with. If you do a visualization of your data and you see that, well, there are a lot of outliers in my data, then going into the values that you'll be predicting, you know that, okay, the mean squared error is not going to help me do justice because there are a lot of outliers. And sometimes these outliers may not just be a case of it is bad data, but maybe that's the actual situation on the ground. There were some values that maybe you are picking temperature, and out of the blue, there were some days it was extremely hot. So those values were very high. Yes, they are outliers. You cannot say that they are wrong data. It is actually correct data. You need to include it. But then if you are building a regression model to predict temperature for the next 1 week, you don't want to be relying on those mean squared errors because of the outliers you have. But then if there are no outliers and your data is very close to each other in terms of the variances, and you have that regression model, then you can be rest assured that, okay, mean squared error is going to help you to actually make a justification for which model is performing better than the other. So the conclusion I'll give over here is, okay, based on what we see, we can confidently say that, okay, and that will actually be unless we plot the data set to actually make that conclusion to say that, okay, there are outliers over here and they are not. Let me try and see if I can data. Data dot data. So this is the actual data as we see over here. And clearly you can see that from the scaling that we see, okay, there are some variances between our data. And let me see if I can see the highest value. Okay, this is a NumPy array. Let me see. Let me try and see if I can convert this into a data frame. All right. So now let's call this data frame X. Good. Now I can do x.describe to see the things I want to see. So x.describe, call this method this way. Good. So this is what I want to see. And these are things like I indicated earlier. We've looked at these things and we can use our knowledge on statistics to see some of these things and make sense out of this. Good. So now we get the counts. We don't seem to have any problem over here. The number of times we have this. Now let's look at the mean. So you see the mean and you see the standard deviation. There's about a 0.00476. Okay, so this is a very small standard deviation, and then the minimum value is what we see over here. The maximum value is what we see over here in terms of these values, and the standard deviation is extremely small with this mean. Now, based on what we see over here, at least with these values of and this is just for the first column, which was age. Okay, this is just for the first column, which is age. We see other ones as well. Okay, I think the other ones too are always, or sorry, are almost the same in terms of their standard deviations. And okay, so in terms of standard deviation, I think all of them are the same. But then when it comes to the minimum value, as we see over here, um, the various columns have different minimum values and then different maximum values and stuff like that. All right. And what is probably accounting for the same standard deviation across board is perhaps maybe the scaling was done with the same factor. Okay. So once again, the difference between remember when I was dealing with the scaling issue, let me say yes, we had 2x, okay, plus 4y. Sorry, 4y was equal to 10. I think that was the example I used earlier on. And we could have scaled everything down by dividing by 2, where we get x plus 2y is equal to 5. Or we could have scaled up by multiplying by 3, where we are also going to get, for instance, 6x plus 12y is equal to 30. Now, the point is, because we are scaling down and scaling up by the same factor, okay, the variations or the standard deviations are also not going to change. That's the point I'm making over here, because over here, if you have to just pick up these numbers, 2, let's say 4, and then maybe 10, okay, if you have to plot this on a number line, the variation between this and this is 2, and the variation between this and this is let's say a 6. Okay, if I scale this down to 1, 2, and then 5, the variation between this and this is the 2, and the variation between this and this is the 3. Basically, what we've ended up doing, it is just the multiplying effect, the factor that's changing. Okay, if we are to look at it from the instance where we have the 6, the 12, and then the 30, in terms of the standard deviation, they are going to remain the same because of the same factor. And that's what we see, sorry, with the standard deviation value we see over here. But then the other ones may change. Now, what it also means is, based on what we see over here, maybe a visualization was probably going to be our best bet to make the explanation very simple over here. But based on the statistics we have from our data set, we can clearly see that, well, because the standard deviation is very small, okay, we can clearly say that there's no, because if there was going to be, or if there was an outlier, then that's going to kick the standard deviation out of the rule. But then this is very small. So we can clearly say that, okay, the variance we have in this is not too much, okay, of a problem as far as this is concerned. There are no outliers, and for which reason the mean squared error is going to be a good measure for we trying to say that this model gave us a very good performance. So in that case, if I'm the one to make a decision, then clearly I'm going to go with the smallest mean squared error, which in this case is not even small, but then comparatively, as we compare with the others, we can see that the support vector machine is giving us this over here. All right. Now, the last thing, because we have just some few seconds left, let me just quickly move on. And what I said was, if you are to, let's say, play the devil's advocate, okay, maybe we don't know what we are doing. We're just building, we saw somebody build a machine learning model and we're just putting things in there. Let's say if I'm to say from sklearn dot, no, not linear, let's say SVM, and I want to import the support vector classifier. This we've seen before. And now let's create a new model. Model is called to this support vector classifier. And then what do we pass? We leave it this way. Now, if I'm to do model.fit and pass in my X train and then my Y train and run this, clearly some model has been built one way or the other. All right. Now, if I'm to do model.predict and I pass in the X test and run this, we still get some values one way or the other. But the point is, you may get these values and you may report on them. And the problem here is, well, this one is working because at least what's at the back of my mind, what is happening here is it is probably seen from the original data set, let's say the X, sorry, from the Y train, okay? It is probably seeing each and every one we see over here as a class of its own. Okay, it is seeing each and every one we have over here as a class of its own. So then we haven't really done what I'll say some proper learning. We have just fitted some values in there, and we saw an example in the case of the SVM when we're dealing with the kernels. Okay, garbage in, garbage out. Once we put something in there and there's no problem, it is going to do some computation. We are later going to see examples of these when we deal with the deep neural networks and the models that comes alongside that. We determine our own architecture and we determine our own model. If you put what is not right, it is almost like asking AI some dummy question. It is also going to give you some dummy answer based on how the question was framed. Okay, and that's how these systems are built. So if we don't train it with the appropriate and the right data set in the right context, things are not going to look good for us at the end of the day. All right. Now, today is Monday. What I want you to do, okay, what I want you to do in terms of exercise is there's also another data set over here. I think from sklearn dot data sets import, there is the California housing data set. Okay, this one, the California housing. Let me see. Okay, I think it should be this one, fetch California housing. So let me call this data is equal to Control C, and then let's instantiate this way. And now it is, yeah. So you have some values over here. Okay. Now let's look at the description because I want you to also build some models of your own and see how you can make things work. So let me print this out so everything is nicely formatted. All right. So you see that this one, the number of instances, very good. This one is quite huge, 20,000 K plus. And then the number of attributes is 8 numeric, okay, predictive attributes and a target. All right. So of course, there are no non-data or missing values. And now the information we see over here is the median income in a block. So this is a census that was conducted at in California in the US, and then they came up with this data. So the median income per household, okay, the house age, that's the median house age in a block group, the average number of rooms, the average number of bedrooms, the population. If you are to go to places like Choco and you do this, you're actually going to see a trend, okay? And some of these things, not just Choco, but even estates, Legon, Trasaco, and all those places, you realize that there's going to be a trend. And for which reason, if you are going to, let's say, buy a house or make some investments, okay, normally the real estate people will probably use this to make informed decisions when it comes to real estate investments. Let's say you have a land, one at whatever and one at whatever. You do not know the place, the location, and the kind of businesses that runs over there. But then if you have a data set of this nature, you can actually build a model to know that, okay, this is how much you may be selling your property for and stuff like that. So it gives you the description we see over here. And then the target is what I'm looking for. But then let's see. So if I'm to do data, we get to see the actual things. Things have been scaled down once again. If you read them, you are going to see. And now if I'm to do data.target, we see that clearly we have numeric values. So this is a very good use case for our regression, okay? And then if I'm to do dot shape, let me see. Okay, once again, this is the 20,000 plus as we see over. So what I want to do, or what I want you to do, is pick up these data sets again from the scikit-learn dataset module, okay, and build some regression models for the ones that we did. So just look at, first of all, look at the linear regression, okay. Then after linear regression, you can look at the decision tree regressor. You can also look at the random forest regressor, and then the support vector machine regressor. I hope this will be a very good exercise, and with just a matter of time, you can complete this in less than 30 minutes, I believe. And just get your results and try and do the analysis. Okay, the values you may not understand, just do a Google search. You may get some information about, okay, if I'm comparing these two values, then this one is better than this. And on Friday, maybe you can share your results, and also we can learn a thing or two why maybe you would prefer a model over the other. All right, please, are there any questions?
Okay, thank you very much, Ken, for the presentation. So, Mariama, do you have any question? Okay, so we...
Please.
Okay, so we bring the presentation or this seminar session to a close today, and then we meet on Friday, and then see. Now we have about we have 2 more weeks to go, because our last meeting will be for the revision week. The week at the end of teaching will be our last meeting. End of teaching will be our last meeting. So after that one, then we are done. What we are going to reflect is we'll see whether maybe during the vacation we may have time that we may want to continue with you. If not, then we'll see how best we can close the chapter. And then we'll rest also for a while, and then we start the new session. What we have outstanding, we have because this year we introduced a number of things, the classifiers and then the regressors in the program. So it has taken us a bit more of the time that we anticipated. So what we will do is I will discuss with Ken again, and we see we now have to move to deep multi-layer neural network model development. And then, yeah, we will move to deep neural, maybe we might even start Friday, the deep neural network model development. Because we have already done some of the things earlier, that will not take us too much time. Then we will figure out whether we may want to also touch on the web app, how we can link it up with the web app development. If not, then we'll move straight away to convolutional neural network. Then if, again, the pace we are going, if we have time, then we'll look at recurrent neural network, which will lead us to the natural language processing model development. So you see that we have a bit of work to do, but I'm trying to see how we can manage this. If not, then when we get to a certain point, we'll just show you we'll give you some of the past audios that we have. And then, because I see that the motivation has come down. Now we have technically about less than 10. Less than 10 people, starting with a large number. So it means that people's interest is going down on it. So maybe the few groups that are there, we'll see how best we can support you in a way, then we'll call it off. Okay. On that note, we meet Friday. And Ken, thank you very much also for the presentation.
You are welcome, sir.